Now, in this lecture, we'll find out the length of line segment X. In the drawing, we have two quarter circles. The two quarter circles touch each other at point B. In addition, we know that line segment AB equals to 1 unit in its length. Line segment QS equals to line segment SP. And our mission is to find out the length of this line segment BC that is equal to X. Okay. So, first of all, we know that this is a quarter circle, and therefore PA and AB, they are both the radii of this quarter circle, and therefore they are equal to each other. And we know that AB equals to 1, therefore PA must be also equal to 1. That is to say, the radius of this quarter circle is equals to 1 unit. In the next step, we join points P and B together by a straight line. By joining points P and P, we created the right triangle PAB. So I copy the right triangle PAB. In the new page, we will implement the Pythagoras theorem in this right triangle PAB. Here by PT is a evaluation for Pythagoras theorem. So actually, this is the right triangle PAB that I copied from the original drawing. In this right triangle PAB, according to the Pythagoras theorem, PB squared equals to PA squared plus AB squared. So PB squared, that is the square of the hypotenuse, equals to PA squared. PA is 1, therefore PA squared is 1 squared, that is 1, plus AB squared. AB is 1, therefore AB squared is 1 squared, that is also 1. So in total PB squared equals to 1 plus 1, that is 2. PB squared equals to 2. We take a root out of this equation and we will get that PB equals to the square root of 2 units. That is to say, the hypotenuse PB here in the right triangle PAB, it is equals to the square root of 2 units in its length. Here we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other. So if we define the size of this angle as alpha, then the size of this angle also must be equal to alpha. And we also know that the sum of the angles in any triangle is equals to 180 degrees, and especially it is true in the right triangle PAB. So which angles we have in the right triangle PAB? We have this angle equals to 90 degrees, plus alpha, that is plus 2 alpha. In total, the sum of the angles in the right triangle PAB must be equal to 180 degrees. So 90 degrees plus 2 alpha equals to 180 degrees. We subtract 90 degrees from this equation, and finally we get that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. Here we divide this equation by 2, and finally we get that alpha equals to 90 degrees over 2 is 45 degrees. So if we found out that this angle alpha equals to 45 degrees in its size, and this is also angle alpha that is equal to 45 degrees. In the next step, we join points Q and B together by a straight line. In this big quarter circle, BC and QC, they are both the radii of this quarter circle, therefore they are equal to each other. And we know that BC equals to x, therefore QC must be also equal to x units in its length. And if we repeat on the same process in the right triangle QCB, we find out that this angle equals to 45 degrees, and this angle also equals to 45 degrees because of the fact that the right triangle QCB is also an isosceles triangle, because of the fact that BC equals to QC in the right triangle QBC. The right triangle QCB is also an isosceles triangle, and we know that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if one angle is alpha, then the other angle must be also equal to alpha. And we know that alpha plus alpha must be equal to 90 degrees, because this angle it is already equal to 90 degrees. So 2 alpha equals to 90 degrees, we divide the equation by 2 and we get that alpha equals to 45 degrees. So those two angles, each of them is equal also to 45 degrees in its size. Okay. And I'll copy the right triangle QCB in a new page, and we will implement the Pythagoras theorem in this right triangle QCB. Here by PT is abbreviation for Pythagoras theorem. This is the right triangle QCB that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle QCB, QB square equals to QC square plus BC square. So QB square, that is the square of the hypotenuse, equals to QC squared. QC is x, therefore QC squared is x squared plus BC squared. BC is x, therefore BC squared is x squared. So in total, QB squared equals to x plus x, that is 2x squared. QB squared equals to x squared plus x squared, that is 2x squared. So QB squared equals to 2x squared. We take out all of this equation, and finally we get that QB, the length of the hypotenuse QB equals to the square root of 2x squared. So QB equals to the square root of 2, and the square root of x squared is x. So in total, QB, the length of QB is equals to square root of 2 times x. So we can write here the original drawing that QB equals to the square root of 2 times x. Okay. In the next step, I present to you rule number 3, and we'll implement rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So in the drawing we have the straight line AB. If we focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to this rule number 3. So which angles we have at the upper side of AB at point Q? We have this angle alpha and the other angle that is beta. So in total, alpha plus beta must be equal to 180 degrees. We can actually implement rule number 3 in our drawing. Why? Because in our drawing, if we focus on the upper side of the straight line AC at point B, here the sum of the angles must be equal to 180 degrees according to rule number 3. So I copy the straight line AB with point B here, and we implement rule number 3 in the straight line AB. Here, if we focus on the upper side of A, the straight line AC at point B, the sum of the angles must be equal to 180 degrees. Okay, so I copy the straight line AC with point B and with its angles, and we implement on this straight line AC rule number 3. So this is the straight line AC with point B and with its angles that I call it from the original drawing. According to rule number 3, the sum of the angles on the upper side of the straight line AC at point B must be equal to 180 degrees. So which angles we have at the upper side of AC at point B? We have this angle that is equal to 45 degrees plus the missing angle that we define as x plus this angle that is equal to 45 degrees. In total, the sum of those three angles must be equal to 180 degrees according to rule number 3. The sum of the angles on the upper side of AC at point B must be equal to 180 degrees. So 45 degrees plus 45 degrees is 90 degrees, so 90 degrees plus x must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and finally we get that x, the missing angle x, equals to 180 degrees minus 90 degrees. This is 90 degrees. So the missing angle here, x, is a right angle. So I can write down in the original drawing that the missing angle PBQ is a right angle. It is equals to 90 degrees in its size. So if angle PBQ, this angle is a right angle, then triangle PBQ is a right angle. So in the next step, I will copy the right angle PBQ in a new page, and we will block this right angle PBQ by a circle. We have a rule that any triangle can be blocked by a circle, and especially the right angle PBQ, we can block it by a circle. So actually, this is the right triangle PBQ that I blocked by this circle. So in the drawing we have a circle, and inside this circle we have peripheral angle PBQ that is equal to 90 degrees in its size. And here we have rule number 5 that relates to any peripheral angle that is equals to 90 degrees in its size. According to rule number 5, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. So in the drawing we have a circle. Inside the circle we have peripheral angle MAN. This peripheral angle MAN is equal to 90 degrees in its size. Therefore, according to this rule number 5, peripheral angle MAN must rest on the diameter of the circle. From the drawing itself, it is very easy to see that peripheral angle MAN rests on chord MN. Therefore, chord MN, according to this rule number 5, must be the diameter of the circle. And indeed, chord MN is the diameter of the circle. Why? Because of the fact that chord MN passes through point O, that is the center of the circle. It must be the diameter of the circle. Why? Because any chord that passes through the center of the circle must be the diameter of the circle. So in conclusion, you can say that because of the fact that angle MAN, the peripheral angle MAN equals to 90 degrees, this peripheral angle MAN rests on MN, that is the diameter of the circle. Any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. We can actually implement rule number 5 in our drawing. Why? Because in our drawing we have the peripheral angle QBP that is equal to 90 degrees in its size. So I write it down. Peripheral angle QBP equals to 90 degrees in its size. Therefore, according to rule number 5, this peripheral angle QBP rests on the diameter of the circle. From the drawing itself, it is very easy to see that peripheral angle QBP rests on chord QP, therefore according to rule number 5, chord QP must be the diameter of the circle. Okay, so here chord QP must be the diameter of the circle according to rule number 5. So if we define the radius of this circle as r, if the radius is r, then the diameter QP must be equal to 2r. The diameter QP equals to 2r. So from one side, QP equals to 2r, but from the other side, it is given as the equation that PS equals to SQ. So if we define PS as x, then SQ must be also equal to x because they are equal to each other. So in total, PQ equals to PS that is x plus SQ that is x. So in total, PQ equals to x plus x, that is 2x. So we can write down here that from one side, PQ is the diameter of the circle that equals to 2r. From the other side, PQ also equals to 2x. This again. From one side, PQ equals to 2r, it is the diameter of the circle. From the other side, PQ equals to 2x according to what is given as the question. So PS equals to SQ. So from those two equations, we derive that 2r equals to 2x. 2r equals to 2x. We divide this equation by 2, and we get that r equals to x. So here, PS that is equals to x according to our definition, it is also equals to r, and SQ that is also equals to r, x it is equals to r. So here, PS equals to r, it is the radius of the circle, and SQ also equals to r, it is the radius of the circle, because r equals to x. And because of the fact that QS is r and PS is also r, so those two radii of this circle touch each other at point S. Therefore, point S is the center of the circle. So we can write here that point S is the center of the circle. Point S is the center of the circle. In the next step, we'll join points S and B together by a straight line. So point S is the center of the circle, point B is the point of the circle itself, therefore SB is the radius of the circle that is equals to R. In conclusion, we found out that PS equals to SQ equals to SB. All those three line segments are the radii of the circle that equals to R. So we can write here that we join points S and B together by a straight line. PS equals to R, SQ equals to R, and SB is also equals to R. This is the radius of the previous circle. Okay, and especially we know that SB equals to SQ, the group the radii of the previous circle, therefore they are equal to each other. So SB equals to SQ. In the next step, we do a construction. That is to say, we complete the big quarter circle to a circle. So this is the big quarter circle that I copied from the original drawing. Now we complete this quarter circle to a circle. We completed the quarter circle to a circle, and we join points Q and B together by a straight line. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule number 13. According to rule number 13, the central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have peripheral angle ASB. This peripheral angle ASB equals to theta in its size, and peripheral angle ASB is subtended on arc AB. In addition, we have in this drawing the central angle AOB that rests on the same, that actually it is subtended on the same arc, arc AB. So in the drawing we have two angles, the peripheral angle ASB and the central angle AOB. Both those two angles are subtended on the same arc, arc AB. And therefore, according to this rule, rule number 3, the central angle is twice as large as the peripheral angle that is subtended on the same arc. So if the peripheral angle ACB equals to theta, then the central angle AOB that is subtended on the same arc, arc AB, must be equal to 2 theta. So the peripheral angle is always twice as large as the central angle that is subtended on the same arc. So if the peripheral angle ASB that is subtended on chord AB is equals to theta, then the peripheral angle AOB that is subtended on the same arc, arc AB, must be equal to 2 theta. So you can actually implement rule number 13 in our drawing. Why? Because in our drawing we have the peripheral angle QSB. This peripheral angle QSB is subtended on arc PQ, the big arc PQ. And we have also the central angle BCQ. The central angle BCQ. This is the central angle BCQ. The central angle BCQ is also subtended on the same arc BQ. Therefore, the central angle BCQ that is subtended on the same arc BQ is the peripheral angle BSQ must be twice as large as the peripheral angle BSQ. Okay, so in order to find out the size of the central angle BCQ, I present to you rule number 6, and we will implement rule number 6 in our drawing. According to rule number 6, the sum of the angles around the point will always add up to 360 degrees. So in the drawing we have point A, this is point A. According to this rule number 6, the sum of the angles around point A must be equal to 360 degrees. So in order to prove that this rule is true, I actually drew a straight line for point A. This is a straight line that passes through point A. And according to rule number 3, we know that the sum of the angles in the upper side of this straight line at point A must be equal to 180 degrees from one side, but from the other side, according to the sum rule number 3, the sum of the angles in the lower side of this straight line at point A must be also equal to 180 degrees. According to the rule, then the sum of the angles on one side of the straight line is equal to 180 degrees. So according to rule number 3, the sum of the angles on the upper side of the straight line at point A equals to 90 degrees, and the sum of the angles in the lower side of the straight line at point A must be also equal to 180 degrees. So in total, the sum of the angles around point A in the upper side and the lower side, in total it is 180 degrees plus 180 degrees, that is 360 degrees, exactly according to this rule number 6, that says that the sum of the angles around point A is equal to 360 degrees in total. So we can actually implement rule number 6 in our drawing. Why? Because in our drawing, if you focus at point C, here the sum of the angles around point C must be equal to 360 degrees according to rule number 6. So which angles we have around point C? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 360 degrees according to rule number 6. Therefore, the missing angle must be equal to 270 degrees. Why? Because 270 degrees plus 90 degrees, in total it equals to 360 degrees. That is the sum of the angles around any point according to rule number 6. So the missing angle BCQ, equals to 270 degrees in its size, according to rule number 6. And because of the fact that the central angle BCQ equals to 270 degrees, and this central angle BCQ is subtended on arc BQ, then the peripheral angle QSB, that is also subtended on the same arc BQ, must be equal to half of this angle, of this central angle. And because of the fact that the central angle equals to 270 degrees, it means that the peripheral angle must be equal to 270 degrees over 2, that is 135 degrees. Okay? So, again, we have here the peripheral angle BSQ that is subtended on chord BQ. Here peripheral angle QSB is subtended on arc BQ, and therefore the center angle BCQ that is subtended on the same arc BQ must be equal twice as the peripheral angle is equal to 125 degrees. Therefore, the center angle must be equal to 125 degrees times 2, that is 270 degrees. Exactly according to rule number 13. Okay, so we know that in triangle PSQ, the sum of the angles must be equal to 180 degrees, and we know that those two sides are equal to each other. So BS equals to SQ in triangle BSQ. Those two sides are equal to each other, and we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this angle is alpha, then the other angle must be equal to alpha also, and the sum of the angles in triangle SPQ must be equal to 180 degrees. So which angles we have inside inside the triangle SPQ? We have 135 degrees. In triangle BSQ, we have this angle equals to 135 degrees plus alpha, that is plus 2 alpha. In total, they must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So we subtract 135 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 135 degrees, it is 45 degrees. So 2 alpha equals to 45 degrees. We divide this equation by 2, and finally we will get that alpha equals to 45 over 2 degrees. So this angle alpha equals to 45 degrees, and this angle alpha also equals to 45 degrees. This angle alpha equals to 45 over 2 degrees, and this angle alpha also equals to 45 over 2 degrees. So here I will copy the right triangle PBQ in a new page, and we analyze this right triangle PBQ. We just right now found out that angle PQB, angle PQB, or angle SQB, that is exactly like angle PQB, angle SQB, this angle equals to 45 over 2 degrees. So this angle equals to 45 over 2 degrees, because this is angle alpha actually. So I'll copy the right triangle PBQ in a new page and we'll analyze it. So actually, this is the right triangle PBQ that I copied from the original drawing. We have already found out that PB equals to the square root of 2 units, side QB equals to the square root of 2 times x. This angle PQB equals to 45 over 2 degrees. This angle PBQ equals to 45 over 2 degrees. So in this right triangle PBQ, tangent 45 over 2 degrees. Tangent 45 over 2 degrees. This angle equals to 45 over 2 degrees in its size. So tangent 45 over 2 degrees equals to PB over BQ. So tangent 45 over 2 degrees equals to PB, that is square root of 2, over BQ, that is square root of 2 times x. So we have square root of 2 in the numerator, and we have square root of 2 in the denominator, so square root of 2 will get cancelled, and we left only with 1 over x. So in conclusion, we found out that according to equation number 1, tangent 45 over 2 degrees is equals to 1 over x. Okay, tangent 45 over 2 degrees equals to 1 over x for one side, but from the other side we have the trigonometric identity that tangents 2 theta equals to 2 tangents theta over 1 minus tangents square theta. We define theta as 45 over 2 degrees. So if theta is 45 over 2 degrees, it means that 2 theta is 45. 2 theta is 45. So in the next step, we'll substitute theta in this trigonometric identity by 45 over 2, and we'll substitute 2 theta by 45 degrees in this trigonometric identity, and we get that tangents 2 theta, and 2 theta is 45 degrees. That equals to 2 times tangents theta, and theta is, according to our definition, theta is 45 over 2. All divided by 1 minus tangents square theta, and theta, according to our definition, is 45 over 2 degrees. So when we found out that, according to equation number 2, tangents 45 degrees equals to 2 times tangents 45 over 2 over 1 minus tangent square 45 over 2 degrees. So in the next step, we will define tangents 45 over 2 degrees as t, tangents 45 over 2 equals to t according to the definition. Repeat again. Tangents 45 over 2 degrees equals to t according to our definition. And now we can substitute tangents 45 over 2 in this equation number 2 by t. We do it now, we get that according to equation number 2, tangents 45 degrees is 1, and it is equals to 2 times tangents 45 degrees over 2, and tangents 45 over 2 degrees equals to t according to our definition. So we substitute tangents 45 over 2 by t, so in total in the numerator we will have 2t, because this expression equals to t over 1 minus tangents square 45 over 2 degrees. If tangents 45 over 2 degrees equals to t, then tangents square 45 over 2 must be equal to t square. So in total, in the denominator, we have 1 minus t square. So according to equation number 2, we found out that equals to 2t over 1 minus t squared. Here we will multiply this equation number 2 by 1 minus t squared, and we get that according to equation number 2, 1 times 1 minus t squared is 1 minus t squared, that is equals to 2t. So here we add t squared to this equation number 2, and we will get that according to equation number 2, 1 equals to t squared plus 2t. Here we subtract 1 from this equation number 2, and finally we get that according to equation number 2, t squared plus 2t minus 1 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b and c are the coefficients of the quadratic equation, and x is the variable that we are looking for, and we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, t squared plus 2t minus 1 equals to 0, the variable that we are looking for is t. Therefore, x equals to t, the coefficient a equals to 1, the coefficient b equals to 2, and the coefficient c equals to minus 1. So we put the data inside this formula for x, and we find out the value or the values of t, because x equals to t. So x equals to t, so here we substitute x by t, and it equals to minus b. b is 2 in our specific quadratic equation, therefore minus b is minus 2 plus minus square root of b squared. b is 2, therefore b squared is 2 squared, that is 4, minus 4 times a is 1 times c, that is minus 1, over 2 times a is 1. So actually found out that t equals to minus 2 plus minus, inside the root we have 4, minus 4 times minus 1 is plus 4, so inside the root in total we have 4 plus 4, that is 8, divided by 2 times 1, that is 2. So we found out that t equals to minus 2 plus minus square root of 2 over 2. So t equals to minus 2 plus minus the square root of 8, and 8 is 4 times 2. So we substitute 8 by 4 times 2, all divided by 2. So t equals to minus 2 plus minus the square root of 4 is 2, so inside the root we left only with 2. So we can find out that t equals to minus 2 plus minus 2 times root of 2 over 2. So t equals to minus 2 over 2 is minus 1, plus minus 2 over 2 is 1, plus minus root of 2. So we found out that t equals to minus 1 plus minus root of 2. So here we have two solutions that are possible for t. The first solution for t is that t equals to minus 1 minus root of 2. And the second solution for t is that t equals to minus 1 plus root of 2. So, according to the first solution, t equals to minus 1 minus root of 2, that is actually, of course, a negative number. But according to our definition, t equals to tangents 45 over 2 degrees. And tangents 45 degrees, tangents 45 over 2 degrees is a positive number. Therefore, t is a positive number because it is equal to tangents 45 over 2 degrees. T is a positive number and it can never be equal to this expression that is a negative number. A negative number can never be equal to a positive number. Again, t equals to tangents 45 over 2 degrees, that is a positive number, and it can never be equal to minus 2 minus root of 2, that is a negative number. Therefore, we cancel this solution, and we left only with the second solution that is left for t, that is t equals to minus 2 plus root of 2. And again, according to our definition, t equals to tangents 45 over 2 degrees. And here it is equals to minus 1 plus root of 2. Okay. So for one side, tangents 45 over 2 degrees is equals to square root of 2 minus 1. This is according to this equation. Tangents 45 over 2 degrees equals to square root of 2 minus 1. This is from one side. But from the other side, we have already found out that tangents 45 over 2 degrees is equals to 1 over x. Here we have according to equation number 1, tangents 45 over 2 degrees equals to 1 over x. So we actually have two different equations for tangents 45 over 2 degrees. And therefore, in the next step, we'll create equation number 3 that states that tangents 45 over 2 degrees, according to equation number 1, must be equal to tangents 45 over 2 degrees, according to equation number 2. Repeat again. According to equation number 3, equation number 3 states that tangents 45 over 2 degrees, according to equation number 1, must be equal to tangents 45 over 2 degrees, according to equation number 2. So, tangents 45 over 2 degrees, according to equation number 1, is equals to 1 over x here. is equal to 1 over x. And it must be equal to minus 45 over 2 degrees according to equation number 2. Minus 45 over 2 degrees according to equation number 2 equals to the square root of 2 minus 1. So actually found out that according to equation number 3, 1 over x equals to the square root of 2 minus 1. Here we multiply this equation number 3 by x. It is allowable to multiply by x. Equation number 3. Why? Because x is the length, and the length can never equals to 0. Here, x is the length of line segment AB and line segment BC. X is the length of line segment BC, and from the drawing itself, you can see that BC is not equals to 0. For that reason, you can multiply equation number 3 by x. And we get according to equation number 3, one equals to square root of 2 minus 1 times x. So here we will divide this equation number 3 by square root of 2 minus 1. And we get that according to equation number 3, x equals to 1 over square root of 2 minus 1. So here we'll multiply both the numerator of this side of the equation by square root of 2 plus 1, and then we divide it by square root of 2 plus 1. And we get that 1 times square root of 2 plus 1 over square root of 2 plus 1 times square root of 2 minus 1. We actually multiplied this side of the equation by 1, because square root of 2 plus 1 over square root of 2 plus 1 is 1. And it is allowable to multiply anything by 1. Therefore, this operation is allowable. And we get that x equals to the square root of 2 plus 1 over square root of 2 minus 1 times square root of 2 plus 1 equals to, according to the algebraic identity, that a minus b times a plus b equals to a squared minus b squared. We will get that square root of 2 minus 1 times square root of 2 plus 1 equals to the square root of 2 squared, that is 2, minus 1 squared, that is 1. So in total, in the denominator, we have 2 minus 1, that is 1. So x equals to square root of 2 plus 1 over 1. So in total, x equals to the square root of 2 plus 1 units. Or in terms of numbers, x equals to 2.414 units. Again, x equals to either square root of 2 plus 1 units in its length, or in terms of numbers, x equals to 2.414 units. And that is the answer to the question. Repeat again, the length of this line segment BC is equal to x. It is equals to either square root of 2 plus 1 units, or in terms of numbers, BC is equal to x is equals to 2.414 units. So in the next step, I'll summarize the lecture. In this lecture, we found out the length of this line segment BC is equal to x. So in the drawing we have those two quarter circles. In addition, we know that AB equals to 1 unit in its length, and we also know that line segment QS equals to line segment SP. And our mission is to find out the length of this line segment BC is equal to X. Okay. So, first of all, we know that this is a quarter circle, and PA must be equal to AB. Both those two line segments are the radii of this quarter circle. So AB is 1, therefore PA must be also equal to 1, because they are both the radii of the quarter circle. Okay? So PA must be also equal to 1. Then we join points P and B together by a straight line. In this way, we created the right triangle PAB. So I copied the right triangle PAB in a new page, and we implemented the Pythagoras theorem on this right triangle PAB. This is the right triangle PAB. This is a copy from the original drawing. In the right triangle PAB, according to the Pythagoras theorem, PB square equals to PA square plus AB square. So PB square, that is the square of the hypotenuse, equals to PA square. PA is 1, therefore PA square is 1 square, that is 1, plus AB square. AB is 1, therefore AB square is also 1 square, that is 1. So in total, PB square equals to 1 plus 1, that is 2. So PB square equals to 2. We took out of this equation and finally found out that PB equals to the square root of 2. Here, the length of the hypotenuse PB is square root of 2 units. Okay, then we have the rule that in front of equal sides in the triangle, there are equal angles. So in the right triangle PAB, PA equals to AB. Therefore, in front of those two equal sides, there are those two angles that must be also equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha. So, and we also know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle PAB? We have this angle alpha plus 90 degrees. In total, they must be equal to 180 degrees, only to the rule that I mentioned. So 2 alpha plus 90, 2 alpha, 90 degrees plus 2 alpha must be equal to 180 degrees in the right triangle PAB. Here I subtracted 90 degrees from this equation, and finally found out that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. We divided this equation by 2 and finally found out that alpha equals to 45 degrees. So this angle alpha equals to 45 degrees in size, and this is also angle alpha that is equal to 45 degrees. Okay, then we join points Q and B by a straight line. Here BC equals to QC. They are both the radii of this quarter circle, therefore they must be equal to each other. So if BC is x, then QC must be also equal to x. And those two angles, they are both equal to 45 degrees. Exactly for the same reason that those two angles equal to 45 degrees. Why? Because we have those two sides are equal to each other, and we have the whole that in front of equal sides in the triangle there are equal angles, so those two angles must be equal also to each other, because they are located in front of equal sides. So this angle is alpha, this angle is alpha. So alpha plus 90 degrees must be equal to 180 degrees. And we repeat on the same process, and we get that those two angles, each of them is equal to 45 degrees. Then I copied the right triangle, triangle QCB in the new page, and implemented the Pythagoras theorem in this right triangle, triangle QCB. So this is the right triangle, triangle QCB that I copied from the original drawing. Here by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, in this right triangle, triangle QCB, QB square equals to QC square plus BC square. So QB square equals to QC square. QC is x, therefore QC square is x square plus BC square. BC is also x, therefore BC square is x square. So in total QB square equals to x square plus x square, that is 2x square. So QB square, that is the square of the hypotenuse, equals to 2x square. We took all of this equation and finally found out that QB equals to the square root of 2x square. The square root of 2x square, the square root of x square is x, so inside the root we left only with 2. So we can found out that QB equals to the square root of 2 times x. So here, the hypotenuse QB equals to the square root of 2 times x. Okay. Then I presented to you rule number 3 and implemented rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of the straight line is equal to 180 degrees. Here we have the straight line AB, so if we focus on the upper side of the straight line AB at point Q, the sum of the angles must be equal to 180 degrees. So each angle we have at the upper side of AB at point Q, we have this angle alpha and the other angle that is beta. So in total, alpha plus beta must be equal to 180 degrees according to this rule, rule number 3. We can actually implement rule number 3 in our drawing. Why? Because in our drawing, if we focus on the upper side of the straight line AC at point B, here the sum of the angles must be equal to 180 degrees according to rule number 3. So I copied the straight line AC with point B with its angles in a new page, and we implemented rule number 3 in at the straight line AC. So this is the straight line AC with point B. According to rule number 3, the sum of the angles on the upper side of the straight line AC at point B must be equal to 180 degrees. So which angles we have at the upper side of AC at point B? We have this angle that is equal to 90 degrees, plus the missing angle that is x, that we define as x, plus this angle that is equal to 45 degrees. In total, the sum of those three angles must be equal to 180 degrees according to rule number 3. So 45 degrees plus x plus 45 degrees, in total it must be equal to 180 degrees. 45 degrees plus 45 degrees is 90 degrees, so 90 degrees plus x equals to 180 degrees. We subtract 90 degrees from this equation and finally found out that x equals to 180 degrees minus 90 degrees is 90 degrees. So the missing angle here, x equals to 90 degrees, it is a right angle. So you can write down in the original drawing that the missing angle PBQ that is equal to x according to our definition, it is equals to 90 degrees. This is a right angle. Then, and because of the fact that angle PBQ is a right angle, it means that triangle PBQ is a right angle. So I copied the right triangle PBQ in a new page, and we blocked this right triangle PBQ by a circle. This is the right triangle PBQ that I copied from the original drawing. We block this right triangle by a circle. We know that any triangle can be blocked by a circle, especially triangle PBQ. Okay? And then, so in the drawing, we have peripheral angle PBQ. This peripheral angle PBQ equals to 90 degrees in its size, and we have rule number 5 that relates to any peripheral angle that is equal to 90 degrees in its size. So here we have rule number 5, according to rule number 5, any peripheral angle is equal to 90 degrees must rest on the diameter of the circle. So in the drawing we have a circle, inside this circle we have peripheral angle MAN. This peripheral angle MAN equals to 90 degrees in size, therefore according to this rule number 5, peripheral angle MAN rests on the diameter of the circle. From the drawing itself, it is very easy to see that peripheral angle MAN rests on chord MN, and indeed chord MN is the diameter of the circle. Why? Because of the fact that chord MN is passes for point O, that is the center of the circle. And any chord that passes through the center of the circle must be the diameter of the circle. So in conclusion, we can say that because of the fact that peripheral angle MAN equals to 90 degrees in size, therefore it rests on the diameter of the circle. MN is the diameter of the circle. We can implement rule number 5 in our drawing. Why? Because in our drawing we have peripheral angle PBQ that is equal to 90 degrees. Therefore, according to rule number 5, here peripheral angle PBQ QBP equals to 90 degrees in size. Therefore, according to rule number 5, this peripheral angle PBQ that is equal to 90 degrees rests on the diameter of the circle. From the drawing itself, it is very easy to see that peripheral angle PBQ rests on PQ. Therefore, PQ is the diameter of the circle. QP is the diameter of the circle. So if we define the radius of this circle as R, then the diameter QP must be equal to 2R. So according to rule number 5, so here QP equals to 2R. Okay. This is from one side. We actually found out that QP equals to 2R. It is the diameter of the circle, according to rule number 5. But from the other side, we know that QS equals to SP. QS equals to SP. It is given as the question that QS equals to SP. So if QS is X, then SP must be also equal to X. So in total, QP equals to QS that is X plus SP that is X. So in total, QP equals to X plus X that is 2X. So in conclusion, we can say that from one side, QP is the diameter of the circle, PQ is the diameter of the circle that is equals to 2R. From the other side, PQ equals to 2X. From those two equations, we derive that 2R equals to 2X. We divided this equation by 2 and finally found out that X equals to R. Here, X equals to R. So, that is to say, PS that is equal to X equals to R, and SQ that is also equals to X, it is equals to R. So actually, we found out that at point S, those two radii touch each other. Again, those two radii touch each other at point S. Therefore, point S is the center of the circle. Okay, point S is the center of the circle. Point S is the center of the circle. In the next step, we did a construction, but before that, we know that point S is the center of the circle. In the next step, we join points S and B together by straight line. Point S is the center of the circle, point B is the point of the circle itself, therefore SB is the radius of the circle that is equal to R. So in conclusion, you can say that PS equals to SQ equals to SB. All those three line segments are the radii of the circle, therefore they are equal to each other. So in the original drawing, we joined points S and B together by a straight line. So SB equals to SQ, and it is also equals to SP. All those three line segments are the radius of the previous circle, therefore they are equal to each other. So, and especially SQ equals to SB. So in the next step, we did a construction. That is to say, we completed this big quarter circle to a circle. So I copied the big quarter circle in a new page here, and we completed this quarter circle to a circle. Okay, so we already found out that SQ equals to SB. They are both the radii of the previous circle, therefore they are equal to each other. Then I joined points Q and B together by a straight line. So this angle equals to 90 degrees. So I copy this angle here. So in the drawing we have here central angle QCB. This is the central angle QCB that is subtended on arc BQ. Again, central angle QCB is subtended on arc BQ. And we also have peripheral angle QSB. This peripheral angle QSB is also subtended on the same arc, arc BQ. And we have rule number 13 that relates to a peripheral angle and a central angle that rest on the same arc, or that is subtended on the same arc. According to rule number 13, the central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have peripheral angle ACB. This peripheral angle ACB equals to theta in its size and is subtended on arc AB. And we also have central angle AOB. This central angle AOB is subtended on the same arc, arc AB. So according to this rule, the central angle AOB is twice as large as the peripheral angle ACB that is subtended on the same arc. That is to say, if peripheral angle ACB equals to theta, then the central angle AOB that is subtended on the same arc, arc AB, must be equal to 2 theta. So we can actually implement rule number 13 in our drawing. Why? Because in our drawing we have the peripheral angle QCB that is subtended on arc QB, and we have the peripheral angle QSB that is subtended on the same arc, arc QB. So we have the peripheral angle and the central angle, they are both subtended on the same arc, arc QB. Therefore, the central angle must be twice as large as this peripheral angle that is subtended on the same arc, arc QB. So what is the size of the central angle QCB? We find out the size of this central angle QCB according to rule number 6. According to rule number 6, the sum of the angles around a point will always add up to 360 degrees. So in the drawing we have this point, point A. According to this rule, rule number 6, the sum of the angles around point A must be equal to 360 degrees. In order to prove that this rule number 6 is true, I draw a straight line from point A. Again, I draw a straight line from point A. And according to rule number 3, the sum of the angles in the upper side of this straight line at point A must be equal to 180 degrees, and according to the same rule, the sum of the angles in the lower side of the straight line in point A must be also equal to 180 degrees. So in total, the sum of the angles in the upper side, that is 180 degrees, plus the sum of the angles in the lower side of this straight line in point A, that is also 180 degrees, it is equal to 360 degrees. Therefore, the sum of the angles around point A in total equals to 360 degrees. So we can actually implement rule number 6 in our drawing. Why? Because in our drawing, if we focus on this at this point C, then according to rule number 6, the sum of the angles around point C must be equal to 360 degrees. So which angles we have around point C? We have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 360 degrees. Therefore, this missing angle must be equal to 270 degrees, because 270 degrees plus 90 degrees equals in total to 360 degrees. That is the sum of the angles around point C according to rule number 6. So the missing angle QCB, this missing angle must be equal to 270 degrees. And therefore, this angle BSQ, must be equal to half of it. Why? Because the peripheral angle BSQ is subtended on chord QB, and it must be half of the size of the peripheral angle QCB that is also subtended on the same chord QB. So if the central angle QCB equals to 270 degrees, it means that the peripheral angle QSB that is subtended on the same arc QB must be equal to half of it. That is to say, it is equal to 270 degrees over 2, that is 135 degrees. Okay? So, we focus on triangle QSB. In triangle QSB, we know that QS equals to SB. Those two sides are equal to each other, therefore it is actually an isosceles triangle. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be also equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha. But we also know that the sum of the angles in any triangle is equal to 180 degrees. Okay, so in triangle BSQ, the sum of the angles must be equal to 180 degrees. So here alpha plus 125 degrees, in total it is equal to 180 degrees. Okay. Again, alpha plus 135 degrees equals to 180 degrees. So here we have 135 degrees plus 2 alpha equals to 180 degrees. According to the rule that the sum of the angles in any triangle, and especially in triangle BSQ equals to 180 degrees. So here we subtracted 135 degrees from this equation, and we found out that 2 alpha equals to 180 minus 135 is 45. So 2 alpha equals to 45 degrees. Here we divided this equation by 2, and finally found out that alpha equals to 45 over 2 degrees. So this again, alpha equals to 45 over 2 degrees. Okay, then I copied the right triangle PBQ in a new page, and I analyze this right triangle PBQ. This is the right triangle PBQ that I covered from the original drawing. We have already found out that side PB equals to the square root of 2 units, side BQ equals to the square root of 2 times x units. and this is angle alpha is equal to 45 over 2 degrees. So in the right triangle PBQ, according to the Pythagoras theorem, tangent 45 over 2 degrees equals to PB over BQ. Again, tangent 45 over 2 degrees equals to PB over PB over BQ. PB is square root of 2 and BQ is square root of 2 times x. So we have square root of 2 in the numerator and square root of 2 in the denominator, so square root of 2 will get cancelled. So this expression equals to, in total, 1 over x. After cancelling square root of 2, it is equals to 1 over x. So in conclusion, found out that tangent 45 over 2 degrees, tangent 45 over 2 degrees equals to 1 over x. Tangent 45 over 2 degrees equals to 1 over x. This is according to equation number 1. While we have the trigonometric identity that tangent 2 theta equals to 2 tangent theta over 1 minus tangent square theta. Then we substitute theta by 45 over 2 degrees. So if theta is 45 over 2 degrees, it means that 2 theta equals to 45 degrees. So we substitute theta by 45 over 2 degrees in this trigonometric identity, and we substitute 2 theta by 45 degrees. And regarding according to this trigonometric identity, tangent 2 theta is 45 degrees equals to 2 tangent theta. Theta is 45 over 2 degrees over 1 minus tangent square theta, and theta is 45 over 2 degrees. Then we define tangent 45 over 2 degrees as t, and we substitute tangent 45 over 2 degrees by t in this equation number 2. And we found out that according to equation number 2, tangent 45 degrees is 1, that is equals to 2 times tangent 45 over 2 degrees. Tangent 45 over 2 degrees is t. So in total, in the numerator we have 2t. So 1 equals to 2t. In the denominator we have 1 minus tangent square 45 over 2 degrees. And tangent 45 over 2 degrees is t, so this expression in total equals to 1 minus t square. So in the denominator we have 1 minus t square. So in total, according to equation number 2, we actually found out that 1 equals to 2t over 1 minus t square. Here we multiply this equation number 2 by 1 minus t square, and we found out that according to equation number 2, 1 minus t square equals to 2t. Then we added t square to this equation number 2, and finally found out that 1 equals to t square plus 2t. Then we subtracted 1 from this equation number 2, and finally found out that t square plus 2t minus 1 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula, that x equals to minus b plus minus 4 of b squared minus 4 times ac over 2a. In our specific quadratic equation, t squared plus 2t minus 1 equals to 0, the variable that we are looking for is t. So x equals to t, the coefficient a equals to 1, the coefficient b equals to 2, and the coefficient c equals to c. The coefficient c equals to minus 1. Coefficient c equals to minus 1. So we put the data inside this formula, and we found out the value or the values of t, because x equals to t. Again, x equals to t, so we substitute x by t, and found out that t equals to minus b. B is 2, so minus b is minus 2, plus minus square root of b squared. B is 2, so b squared is 2 squared, that is 4, minus 4 times a times c. So minus 4 times a is 1, and c is minus 1. So it is minus 4 times minus 1 over 2a. A is 1, so 2a is 2 times 1, that is 2. So t equals to minus 2 plus minus, inside the root we have 4, and minus 4 times minus 1 is plus 4. So in total, inside the root we have 4 plus 4, that is 8. And therefore I actually found out that t equals to minus 2 plus minus square root of 8 over 2. So t equals to minus 2 plus minus 8 is 4 times 2 over 2. The square root of 4 is 2, so 2 equals to minus 2 plus minus the square root of 4 is 2, so inside the root we left only with 2. So in total t equals to minus 2 plus minus 2 times square root of 2 over 2. 2 minus 2 over 2 is minus 1, and 2 over 2 is 1. So in total t equals to minus 1 plus minus square root of 2. So here we have two solutions that are possible for t. The first solution for t is that t equals to minus 1 minus square root of 2. And the second solution for t is t equals to minus 1 plus square root of 2. But according to our definition, t equals to minus 45 over 2 degrees. That is a positive number. So t that is a positive number can never be equal to minus 1 minus square root of 2, that is a negative number. Therefore we cancel the solution and we left only with the second solution that is possible for t, that t equals to minus 1 plus square root of 2. And according to our definition, t equals to minus 45 over 2 degrees. And it is equals to minus 1 minus square root of 2. So according to this equation number 2, we found out actually that minus 45 over 2 degrees equals to the square root of 2 minus 1. This is according to equation number 2. While according to equation number 1, we have already found out that minus 45 over 2 degrees equals to 1 over x. So we have two different equations for minus 45 over 2 degrees. Therefore we created equation number 3 that states that tangent 45 over 2 degrees according to equation number 1 must be equal to tangent 45 over 2 degrees according to equation number 2. Tangent 45 over 2 degrees according to equation number 1 is 1 over x. It must be equal to tangent 45 degrees over 2 according to equation number 2, that is square root of 2 minus 1. So in conclusion we found out that according to equation number 3, 1 over x equals to the square root of 2 minus 1. Here we multiply this equation by x and found out that 1 equals to square root of 2 minus 1 times x. Here we divided this equation number 3 by square root of 2 minus 1, and finally found out that x equals to 1 over square root of 2 minus 1. So x equals to the square root of 2. So here we multiplied this side of equation number 3 by square root of 2, and then we divided by square root of 2. Actually multiplied by 1, that is, therefore this operation is allowable. So we change nothing. So square root of 2 plus 1 times square root of over square root of 2 plus 1 times square root of 2 minus 1. So in the numerator we have square root of 2 plus 1, and square root of 2 minus 1 times square root of 2 plus 1, according to the algebraic identity that a minus b times a plus b equals to a square minus b square, it will be equals to the square root of 2 squared, that is 2, minus 1 square, that is 1. So in total in the denominator we have 2 minus 1, that is 1. In the numerator we have square root of 2 plus 1. Square root of 2 plus 1 over 1 is square root of 2 plus 1. So in conclusion found out that x, that is the length of this line segment 97 BC, equals to either square root of 2 plus 1 units, or in terms of numbers, x equals to 2.414 units. Okay, thank you very much.